G'day everyone, welcome to week 3, and we're going to carry on from last week's content, which was all about straight lines, about y equals mx plus b, with the only difference being, for starters, that we're now talking about not just y and x, we're talking about applied variables. So it could be distance and time, or cost and number of units made. Anyway, we're going applied instead of just x and y on the Cartesian plane. So firstly, we're talking about y-intercept. Now we knew y-intercept last week. We had a graph like this, and we had y, and we had x, and whatever the line was, we just defined the y-intercept as the number where the line crossed the axes. Well, this time it's still just going to be the number where it cuts the axes, but it's going to mean something. Like, look at this first one. It's a very simplistic graph of taxi cost versus distance travelled. You can see, obviously, as the distance goes up, as the distance gets larger, the cost goes larger, hence it's a positive gradient. But look at where it started. That said, when distance was naught, we had a y-intercept of $2.50, or really in this case I should say a c-intercept because it's the cost axis. And what's the units of the cost axis? Dollars. So now we've got a different letter for the axes and also some units. Clearly this one's saying it's got a y-intercept of $2.50, which means when distance was naught, as soon as we hopped in the taxi, it cost us $2.50, and then for each kilometre we went, it jumped up by a certain amount. Well, that's gradient, the next bit. Another one for y-intercept. This one's another simplistic graph of profit versus number of items sold. And you can see that, well, it's a positive gradient, so for every item sold, the profit went up a certain amount. For every item sold, profit went up the same certain amount. Again, that's the gradient, which we'll look at next. What's the y-intercept mean? Well, it says profit in dollars, so it's negative $200. So we don't normally talk about negative dollars, but in terms of profit, yeah, it's a loss. A negative $200 profit, saying, look, if I make no items, my profit is minus $200. So maybe it's per week or something. So that might be the running cost per week of the factory, what have you. And we need to sell a certain number of items before our profit is zero, otherwise known as our break-even point. And then beyond that number of items, we'll start to make a profit. Okay, so the y-intercept literally means the starting point. When time equals naught, distance equals naught, number of items equals naught, whatever the axis is called is equal to naught, that's our starting amount, that's our y-intercept. Now let's check on the applied meaning for the gradients. We're still calling the gradient m, we called the y-intercept b and the gradient m, same as last week, but again, it'll mean something. Let's look at this graph here, which has got distance versus time. Say it's a car. Okay, we've travelled 3 hours, we've gone 270 kilometres. The line is a straight line. That's all we're dealing with. In other words, it's a constant speed. Okay, it's not accelerating or decelerating. It's just in 3 hours I've travelled 270 k's. So just through common sense, we can say, well, if you travel 270 k's over 3 hours, 270 divided by 3, that's 90 k's each hour if you're at a constant speed. Well, that's the gradient right there. The gradient here, what's the meaning of the gradient here? It's our speed. How do we work it out? Same as last week, rise over run. You draw a triangle anywhere, and here it's a clear triangle. We're only given that it goes through the origin, goes through 3,270. So the vertical rise is 270 kilometres, the horizontal run is 3 hours, and so when I put my vertical rise on horizontal run, if I just look at the numbers, it's 270 on 3, which is 90. But again, if I want to know, well, what does it mean? Just look at the units. If the rise is kilometres and the run is hours, clearly the units are kilometres per hour. Or I could have just done it all in one go. I just could have said the rise is 270 kilometres, the run is 3 hours. Clearly that means 90 kilometres per hour. Okay, so if we're ever asked in a question, an applied one, what does the y-intercept mean and what's the gradient mean? Well, the y-intercept means just look at the number that it's at and the units of the y-axis. If we ask for the gradient, just do rise over run, but don't forget its units. Okay. In the next one here, we've got cost versus number of items. So okay, it's some sort of little company going on. Here I've done it separately with the numbers and the units, but of course we can do it together. What's the gradient mean? Well, the rise, you look at this triangle here, it went up $400. So the rise is $400. The run is 50 and the units is items. Okay, 50 items. what's $400 divided by 50 items? Well, the 400 on 50, clearly that's an 8. 850 is a 400. And the units are dollars per item. Same as this forward slope here, forward slash. That means per, that's like the bottom of a fraction. It was 270 kilometres per 3 hours, hence it's 90 kilometres per hour. It was $400 per 50 items, hence it was $8 per item. So we can get our applied meanings of our gradients. On to the next page, we've got another taxi issue. And it's just an example. We've got a few more numbers shown here. And let's look at the sort of questions we might get asked. We could get given just this graph. And first we ask, well, what's the C-intercept? Well, we know it relates to the y-intercept. It's just the y-axis is a c-axis in this case. The intercept is where it cuts. And so the c-intercept is 2.50 and the units are dollars. So it's $2.50. Then it could say, well, what did that mean? Well, it's always, that's the starting point. In this case, the initial fare. No distance travelled. It costs us $2.50 just to hop in before we start adding on more money. So the c-intercept is initial fare of $2.50. Then we need to work out the gradient. Okay, well the gradient, I'll draw a triangle. What I'm going to do is draw it here. And you'll see, okay, in this triangle here, my horizontal run is 5 and it's kilometres. My vertical rise, I went from $2.50 to $21. That's what I'm doing here. I'm subtracting $2.50 from 21. In other words, it went up $18.50. So what's the gradient? Well, it's $18.50 on top, we've got here. It's 5 kilometres on the bottom, which I've got here. $18.50 on 5 is $3.70, and it's dollars per kilometre. So we've got two things happening here, which is going to happen in most of our examples in this lecture. Some sort of initial fare. It's a fixed cost. No matter how far you go, it costs $2.50 to hop in. And then there's a gradient, which represents some sort of variable amount. Not sure how much it's going to cost. It's $3.70 per kilometres, but the variable part is how many kilometres did we go. So if I'm trying to find what's the equation of the whole function, it still all comes back to last week's y equals mx plus b. Y was the whatever the y-axis was called, x was whatever the x-axis is called, m was the gradient, and b was the y-intercept. Now in this case, it's not the y-axis, it's the c-axis. So let's replace y with a capital C. Equals, the gradient we just said is $3.70 per kilometre. You don't have to put the units in the equation. That gets pretty messy. It doesn't matter whether I put 3.7 or 3.70. That means the same thing, okay? I'll put 3.70 just because a lot of people are more comfortable with that when we're talking about money. Instead of $3.7, I'd rather see 3.70, but it means the same thing. Times an x, well the x-axis is actually called a d-axis, plus b, okay, the b here is the c-intercept, normally known as the y-intercept, which was $2.50. And let's look at this equation we've got. This equation is the equation of that line. Exactly what we did last week. It's just we changed some letters. Now what does that equation do for us? Well, it starts with c equals. That tells us the cost of any fare we're going to get. This $2.50 cost is what we call fixed, because no matter what, it's $2.50. This part, this 3.70 times d, well, that's variable, because it depends how many kilometres you go. That cost will vary. So, note the things down here, we've got the fixed versus variable, and all I'm doing there is locking in that the fixed cost is always the initial fare. The fixed cost is the y-intercept. You can lock it in. And the variable cost is always the gradient. It's the one that has to get multiplied by whatever the x-axis value is to find out, well, like in this case, how far did I travel? Well, I better times that by the cost per kilometre. Okay, let's go to this example down the bottom here. Okay, so this next one is not graphical. You could sketch it if you're a visual person, that's great. But it's just given to us in words. Let's read it through. The trip charges for a car hire company of $4.60 plus 90 cents per kilometre. Unrealistic, okay, but I'm just making up numbers here. Determine equation for the cost of hire, cost C of hire, where D represents distance travelled. So it's very similar to the previous one, and all it says is determine an equation. So as I said, we could do it graphically, give a bit of a sketch. Firstly, let's do it the way I've done it here, and let's just go for it. Let's do it without a sketch and look at what information they've given us. They've told us the charges are $4.60. That must be the fixed amount. So the fixed cost, in other words, the Y-intercept, little b, is equal to $4.60. Alright, great. 90 cents per kilometre, that's the gradient, because that's how much it rises. For every kilometre I go along the x-axis, for every one I go across, it goes up 90 cents. One across, up 90 cents. That's the gradient. So flowing off the last one, we know our y-intercept is 460 and the gradient is 90 cents. Don't fall for a trap here. Clearly we need the same units, okay? If I just write 90 here, it's not $90 per kilometre, not getting on that one. It's 90 cents. Now, two options. You can either write them both in dollars or both in cents, and it really makes no difference. I'm going to stick to dollars. Instead of 90 cents, I'm going to put 0.9 because it's $0.9. Again, you can put 0.90 if that's what you prefer, but it doesn't matter. And anyway, you can get rid of the units once they're the same because we don't chuck the units into the equation. So I'm going with a y-intercept of 4.60 and an m gradient of 0.90. Now I just go back to every straight line equation comes back to y equals mx plus b. What's the y-axis in this case? Well, it's the cost of hire. That's the subject of the equation. Instead of y equals, I'm trying to find an equation for c equals. I'm not trying to find an equation for d equals, the distance. We're trying to find, it says, determine an equation for the cost c of hire. So c, I'm going to make my y-axis. D is my x-axis. The m is 0.90. And the b is 4.60. There's the equation. Without doing any sketching, our cost is equal to 0.90d plus 4.60. Now, look at the way I've written it here. I've written it seemingly back to front. The point is it doesn't matter. 2 plus 3, 3 plus 2, it's the same answer. When you add things, it doesn't matter which order you get put in. But you might find it logical to think, to not even use this y equals mx plus b method, just to think, well, the cost of getting into this hire car is $4.6 plus $0.9 times d. So for every distance I go in kilometres, I times the 0.9 by it. So both of these answers are the same thing. Okay. So hopefully that makes sense. How are we going to convert these sentences into equations? C equals 0.9d plus 4.6 or 4.6 plus 0.9d. Again, I did say, what if you're a visual person and you wanted to do it graphically? Fine. I'll just do a thing here, make it look like the previous one. I've got a cost axis and a distance axis. I know my cost started at $4.60, so I'll put my units of cost in dollars. I know my distance axis is in kilometres, and I know for every 1 kilometre I go up 90 cents, 0.9. In other words, $4.60 becomes $5.40, becomes $6.30 and $7.20 and so on. Yeah, it's a constant gradient of getting bigger and bigger and bigger as we go up. There's just a bit of a sketch, and so I know that that the gradient of the triangle, I know that the gradient is 0.9, and then I can just go for the equation. I know it's the initial value plus the gradient times by the distance. Okay, if the sketch helps, fantastic, but we don't actually need it. Let's look at the next page. Okay, another example. This time we're given the sketch, we're not given the words as such. We're not given the gradient and the y-intercept like we were last time. We're just given the graph. Okay, let's read it. It's another one, very simplistic. That's all we do, okay? A criminologist studying crime in a city found that the number of crimes committed per week, called C, decreased as the number of police patrolling the city P increased. Okay, crimes decreased as the number of police increased. Fair enough. The following graph shows the relationship between C and P. Determine an equation for the relationship between C and P and explain the meaning of the gradient M and the y-intercept B. Okay, so this is, again, it's just like last week, find the equation of a line. Now last week, if we looked at this, we wouldn't have had units and the numbers wouldn't have been so large. But last week maybe we would have had a line. We might have said, look, it passes through 1, 4. we might have also said it passed through 3, 2. And we might have asked the question, well, what's the equation of the line? And last week we would have said, well, if you've got 2 points, you can find the gradient. Okay, you can do a triangle, and you can say, well, the gradient is rise over run. In this case, it's negative gradient because it's fall over run. It's a minus 2 over 2. So the gradient of this line is minus 1. Then we would have said, what's the y-intercept? In this case, I couldn't read it off because it's only a sketch. But last week we would have said, well, y equals mx plus b. I know the gradient. X is x and y is y. I don't know what b is. So we better, if we know any point the line goes through, we can sub it in. Last week we would have picked one of the points. It doesn't matter whether we pick 1, 4 or 3, 2. I'll pick 1, 4, which means an x value of 1 works with a y value of 4. Okay, 1, 4. So I'm going to sub the y, sub 4 into the y. The m I know is a minus 1. The x I know is a 1 plus b. Again, this is just, I'm just making it up on the spot. I'm not doing the problem on the left yet, I'm just making up one like last week. That gave me 4 equals, or minus 1 times 1 is a minus 1. To get rid of the minus 1 from this side, I'll add 1 to both sides. b equals 5. Okay, so now that I know what m and b are, I can just write the equation line. Y equals m is minus 1 times x plus b of 5. Does it look like the b was going to be 5? Looks pretty good to me. Okay, we're no different. That was last week. Let's do it now with this week. Let's find the gradient of this line. Now I've got 3 points. I don't need 3 points. I'll pick any points I want. I'll follow on with what I did here, which is, looks like I picked, whoop, press P. Looks like I picked these 2 points. As good as any. And I said, let's find the gradient. So here I've used the formula, just to do something different. I'll use the triangle. The triangle, what's horizontal run? It went from 50 to 250, well that's 200. What's the vertical rise? It went from 2,500 up to 3,100. Well, that's a gap of 600. So here, manually I'm looking at it saying, I know it's a negative slope because it dropped 600 at a run of 200. What's minus 600 on 200? Minus on a plus is a minus. I can cancel some zeros, and 6 on 2 is 3. Yes, it's a gradient minus 3. And the formula got us the same thing. As for the y-intercept, I need the y-intercept as well. And I could look at that and say, look, so it looks exactly halfway between 3,000 and 3,500. But in this sketch, we're not actually shown that that's exactly what it is. So I don't want to assume that. If it actually hit right on a certain point, okay, yeah, fine. But when it hits between 2 points, I can't just assume it's halfway. So I'm going to do exactly what we did with that last week example. I know a gradient and I know a point. Let's just choose the point like what I've done down here. I just used the first point, which was 50, 3,100. In other words, that's an x value and that's a y value. I could call it a c value and a p value, but at the moment, just x and y will do me. I'll bring the c and p in at the end. I'm just going to say y equals mx plus b. I can use the y value as 3,100, the m is minus 3, the x is 50, and plus b, well that's the thing I don't know and want to find out. 3,100 equals what's minus 3 times 50, well that's minus 150. And then, how do I get rid of a minus 150? I add 150 to both sides, which gives me 3,250 equals b. So yes, it was exactly halfway in the middle. I couldn't assume it, but it was anyway. Okay, so my equation in terms of y equals mx plus b would be y equals, replace the m with a minus 3, plus b is actually plus 3,250. But don't forget, that was last week. We're not y's and x's this week. The y is a c, and the x is a p. So y equals minus 3p plus 3,250, and we found our equation. So the first thing said, determine an equation for the relationship between c and p. Done. Explain the meaning of the gradient m and the y-intercept b. Well, the gradient m is minus 3, but it's applied one. There must be some meaning behind it. And to me, the meaning, it's all about, just put the units on there. I wrote minus 600. What were the units? minus 600 crimes per week. And what was the 200? Well, that was police patrolling. So just think about, it's minus 3 crimes per week per policeman patrolling, not trolling. In other words, there's a drop of 3 crimes per week for every single policeman patrolling. There's the answer. We dropped 3 crimes per week, minus 3. There were 3 less crimes per week for every policeman added to patrol. There's our applied meaning. So there's the gradient. What about the y-intercept? What did 3,250 represent? Well, again, simplistic. It meant if there were no police patrolling, we would have had 3,250 crimes per week happening. I think it may have been more, in real life, but there we go. The initial value was 3,250 when the horizontal axis was 0. In other words, no police patrolling would have given us 3,250 crimes per week. Okay. Another example, we've got a profit for a company. Now, as soon as I see this, I see the main trap, in my opinion, and that is they're not always drawn from 0. That graph looks like it's got a y-intercept of 500, but the y-intercept isn't just the number where the line hits, it's where it hits the p-axis. The actual p-axis here is actually 300, 200, 100. It's actually over here, because I know I'm not good at drawing on this. Now, what's really going to happen? Well, maybe it's going to be a negative number. I cannot see the actual y-intercept, because the y-intercept happens when n equals 0, not when n equals 300. So that's okay. All I'm saying is we're going to have to use our algebra to find our y-intercept, because I just can't read it off the graph. I couldn't even read it off the last graph. Okay, when it was 3,250, I couldn't promise that, so let's just go with this. Now, have we got 2 good points? Now, when you're trying to find 2 points, like, note this point here, I'm not going to use that, because I can't tell, is it halfway or not? I don't know. You always choose points that go exactly through what I call crosshairs. I'm thinking about, the target sort of stuff. Crosshairs, and if you can spot the thing that's right in the middle, like, I'm not going to use that point, but I'm okay with using that point, or that point, or that point, or that point. The 4 points I've circled, they're all easy to read. And normally, let's see if I did it here, normally I'll choose the endpoints out of habit. And that's what I've done. I said this is the point, an x of 900, comma, and a y of 2000. That's a point. This point, well, that's an x of 300 and a y of 500. So, yoink, yoink, that's where they came from. I grabbed 2 points off the graph. Then let's just do what we've done. We sub into the formula. Y2 minus y1 is 2000 minus 500 is 1500. X2 minus x1 is 900 minus 300, which is 600. And 1500 on 600 is 2.5. We've got ourselves a positive 2.5 gradient. In other words, for every 1 we go across, we go up 2.5. Okay, it's hard to see because, we're showing it at such a scale that that's 100 across. And that's 250 up. 100 across, 250 up. But that makes sense. Okay. Now choose any of the points we want to sub into good old y equals mx plus b again. If we know a point, and here I'm just using the point, the 300, 500 point. So the 500 is the y, so replace y with 500. The 300 is the x. The m we just said was 2.5. And the b is, I don't know. I think it's down here somewhere, but I don't know. Okay, 500 equals, well, 2.5 300s, that's 2 300s, 600, plus half of the 300 is 150, so that's 750 plus b. In order to get that b by itself, I better get rid of this 750, take 750 off both sides, gives me minus 250 equals b. So it looks like my sketch wasn't as bad as it looks. Yeah, my y-intercept really is minus 250, it's down there. So if I make no items, I was making a loss of $250 per week. Ouch. So the equation, when we put it all together, initially I might say y equals 2.5x minus 250, because the y-intercept is minus 250, the gradient's 2.5. But then I would have replaced the y-axis as really a profit axis, and the x-axis really is a number of items, so p equals 2.5n minus 250. And the applied meanings, well, the gradient was 2.5, which meant the number 2.5 is 2.5 over 1. Let's look at the units. 2.5 over 1 means the top $2.50, the 1 is one item. In other words, the profit is increasing at $2.50 per item. For every item we sell, we make a profit of $2.50. And the Yintercept meant, I actually said it before, if we make no items, we're losing $250 per week. Cool. Okay, line of best fit. Now, we've been looking at very simplistic ones where all the dots lie on the line, everything's perfect, and, well, in real life, of course, it isn't always perfect. Now, if we're looking at real data, called empirical or experimental data, as in just real life, experimental data sounds like you actually do an experiment, but even if I just do a survey, ask people questions, and then plot their answers of their heights and their weights or something like that, I might be trying to say that, look, I reckon the taller you are, the more you weigh. So I might do heights there and weights there, and someone might have been 50 kilos and 1.6 height. Someone might have been 90 kilos and 1.8 meters high. So that, that might be my experiment. Am I going to get a perfect line? Am I assured that a 70 kilo person will be 1.7 meters in height? Absolutely not. We do vary in width a little bit too. So I might get some sort of relationship, but I don't know. I'm not going to be an expert at heights, but I reckon it's probably not curved. I reckon we get people more than 100 kilos who aren't 2 meters tall. Anyway, we actually in this course are only dealing with lines of best fit. It's clear, it's worthwhile talking about, of course, some things go to a curve, some things will come back and be an upside down parabola on that. But we only care about straight lines. Okay. So a line of best fit is when you've got all these dots and you want to fit it as best you can. I did my survey, my question asking, whatever, and I just want to put a line through them. Now, that's a bad line. That's a bad line. It's something like that. The third line did something that sort of goes through the center of all of them. And so it's up to you, but in this course, people are going to get different answers in assignments or in the final exam and stuff like that. But within a reasonable limit, hopefully. Look at these 3 lines I've drawn here. They're all good. We basically try and get half of the points above it and half the points below it. Again, I'll do this again. Say 4, 5, 6, half above and half below. That's not a good line. Okay, I've got 3 above it, say, and 3 below it, 3 to the left, 3 to the right, but clearly it's not a good line. You can see, just put the line there, you can see that, no, look, it's going here. And I've only got 4 above and 2 below, but it's just a rough guide that I really want to just get it going in a similar direction to what the points are showing me. So that's a line of best fit. There's software that'll help us get the best line of best fit, as in literally calculate the line that is closest to all the points. We're not going there. We're just going to put in ourselves. Okay, here's an example. We just get given some data points which we can sketch, and this one's already been done. And then we fill in a line, and yeah, we all might get a slightly different line, but hopefully we're really talking slightly different. Here we had an experiment where we measured the height of a eucalyptus seedling. We bought it at 32 centimeters high at 0 days, and we planted it, and then it kept growing, not by the same, it looks like it grew 6 centimeters in the first 10 days, and then it grew 9 centimeters in the next 10 days, and okay, there's a bit of variation, but look, when we sketch it, okay, here's my line of best fit. Now note initially you might think, well, that's the Y-intercept, because it started at 32 and the Y-intercept is the starting point. This is where we vary a bit. There's real life stuff and there's the theoretical stuff. If someone asked me what was the initial height of the plant, I could say, look, it was 32 centimeters. But if I draw a line of best fit, then suddenly all I care about is that line, not the dots. Once I've drawn the line of best fit and someone asks me to find the equation line of best fit, I don't care about where any of the dots are, I care about the line. So let's look at that and care about the line. Where is the Y-intercept of the line I drew? Well, it looks to me like it's about 30ish, maybe even 29. Well, let's just find 2 good points. Like I said with the crosshairs, let's find any points that go right through the crosshair. And I've chosen 0,29. Well, that's stupid. I just did an estimate there. Well, that's... Let's see if I can get... See, normally I like that point. That looks like there's the crosshairs. So does that. Even those two. It is good to get ones that are far apart, because you'll get less error. But you can see here, it's very unmathematical in a way. But we're just okay to do estimates, because my line, I could have drawn it there, on a few different slopes. So we're okay in this. It's not an accurate one. This is just an estimate. I've estimated it cuts at about 29. Rightio. And then here I've said 60,92. Let's check. 60,92. Yeah, that looks about right. And so I've gone for my furthest left point, my furthest right point, just to try and be as accurate as I can. So what's my gradient? Well, I just stick all the numbers in. 92 minus 29 on 60 minus 0 gives me a gradient of 1.05. And others might have gotten slightly different, but we'll all be about that. And my y-intercept, curly equals means approximately equal to, which we're okay to do in this stuff. Hence, line of best fit here is, I've got my h is my y-axis, my t is my x-axis, my gradient's 1.05, and my y-intercept's 29. That's me subbing into y equals mx plus b. Now, we can be fairly confident in interpolating data, as in if someone says, using your line of best fit, tell me roughly how high the seedling would have been by 35 days. And I'll say, well, when t is 35, or here, let's use this question. After 15 days, chuck t equals 15 in, and 15 days, the graph tells me that it's about 44.75 centimetres. About 45 centimetres, great. But what about if someone says, oh, tell me about this height of it after 200 days? And I say, oh, 200, well, that's 70, 140. It's out about here. Do I really trust that it's a straight line? Do eucalyptus trees really grow at the same rate forever and go infinitely high as long as they exist? No, they don't. The reality is here, you can see I've got it down here a bit, that okay, it might be fit by a fairly straight line during the first 10 years, but after that, you've got a sort of limiting height. So the point of this is, and we don't go into much, it's just a bit of stats background, we're going to make a line of best fit and we're going to do estimates, okay? We might get asked about, use your formula now to calculate for t equals 15. But we need to know that if someone asks us about t equals something beyond here, even 80 days, 90 days, 100 days, we'll give you an approximation, but we don't attach a promise to it, okay? We can't, because our experiment is only accurate between 0 and 60 days. Beyond that, I'm guessing. Okay. Okay, so I've got an exercise here. Table shows the progressive score, total runs of a cricket team playing in a one-day 50-over match. If you're not a cricket person, don't get put over by things like this. It's not going to get too technical. We're going to plot points, we're going to draw a line, we're going to find gradient and y-intercept. So if any topic is not in your realm of interest, it's not going to matter, okay? I believe. You can tell me if I'm wrong. We've got some points like number of overs is the n-axis and runs scored is the r-axis. Okay, so number of overs, 7, all right? If that's 5, that's 5, 6, 7. Goes with run scored of 60. Now you want to work out, like here I could see that the gap between 5 and 10 is 5. There's 5 boxes, so that's clearly 1 per box, 5, 6, 7, 8, 9, 10. What about on the y-axis? It's 0 to 20 and there's 5 boxes. 20 divided by 5 is 4, so that's where I see that, each box is worth 4. So that's like a 4, an 8, a 12, a 16. I don't have room to write it, drink time. But we can see it's 4 per box on this side and 1 per box on this side. So 7 overs was here, run scored 60, well that's slap bang on there. There's a point. 17 goes with 87, so 15, 16, 17 goes with 87. Well there's 80, there's 84, there's 88, so 87's about there. Again, it's not, fully accurate. We're doing the best we can. 20 goes with 105. 20 with 105. There's 100. That'll be 104. 105 will be just past that. 25 goes with 123, 25 with 124 is that, so 123 is about that. 33 with 144, 33 will be 30 plus 3, now where am I going to? 144 will be one box up. Did I get it right? 33 is 3 off that axis, 144 is 1 off that. And then 45 goes with 172, 45, 160, 164, 168, 172. So there's 45, 172. Now we're all going to draw a bit of a different line. Do I have anything ruler-esque? This pizza lid looks like it might do. It's better if you've got a clear ruler. I wish I had one. I'm not at work. And let's pretend this is a ruler, because then you can see how many dots you got below and above the line. I'm just going to try and do my best and go, oh, this is rough. It's not the worst. I wish I'd drawn a little bit higher, but God, if we're on an exam, that's fantastic. Okay, now on the next page I know we'll have drawn a different line, but I'm going to leave that. You can read through that. I'm going to go with the line I've got. Okay, graph this data and construct a line of best fit. Done. Find the equation of the line. Well, I need a gradient and a y-intercept. My y-intercept here is, I'm going to call it 40. By the way, I deliberately tried to draw it through 40 to make it easier. The gradient is, well, let's grab that point and let's grab something. I'm just going to grab that. I'm going to call that point an x of 50 and a y of, look, that's 184, 188. Someone might call it 187, trying to be particularly accurate. I'm just going to go 188. Okay, so I've got a point down here which is 0,40, and I've got a point up here which is 50, 188. So my gradient is vertical rise over horizontal run. It's gone from 40 up to 188, which is a 148 rise. It's gone from 0 to 50, which is a 50 run. I'm going to put the units there just because I'm interested in later. I'm probably going to get asked what did they mean. As 148 was runs, and it's 50 overs. So clearly it's runs per over. What's 148 divided by 50? Well, it's nearly 3. It's a 2.9. Let's just go in for it. 148. We'll put it divided by 50 in the calc, and we'll see it's 2.96. That's okay. 2.96 runs per over. For the sake of the equation again, I don't need the units, but I'm just going to write that later. And I know that the y-intercept was 40 runs. Let's just write the equation. Instead of y equals mx plus b, y is an r, m is a 2.96, x axis is an n axis, plus b is a 40 runs. There's the equation of that line. It started at 40 and it went up with the gradient 2.96. Great, perfect. Find the equation of the line, done. Use this equation to estimate the final score after 50 overs. Well, n is the number of overs. In other words, when n equals 50, I can see the final score. It's going to give me 188 because I actually used that point. But let's just play with the formula. I'll show that it's true. R equals 2.96 by n of 50 plus 40, which I assure you will come out to 188. So the equation estimates the final score after 50 overs of 188. Yours or mine on the next page might be slightly different. Use a line of best fit to estimate the over in which the team score reached 100. Let's look at the equation again. R equals 2.96n plus 40. Now it's asking us, what is the n for when R is 100? We can do that. In other words, replace the R with 100, leave the n alone and try and find it. We've got to do a bit of algebra. I want to get this n by itself. The first thing I do is get rid of this plus 40 by minusing 40 from both sides. That gives me 60 equals 2.96n. Then, that's 2.96 times n. I don't want it there. I want to get rid of this times 2.96. So I'm going to divide both sides by 2.96. So n will equal 60 divided by 2.96, which is equal to, trusty calc, 60 divided by 2.96 equals 20.7, no, 2702702, blah, 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 blah. I'll just do 20.3. It was 2.27, so the two rounds up. 20.3. I'm just going to write 1 dp because I rounded it. And that was n. N was measuring overs. In other words, after about 20.3 overs, the score, the equation reckons the score will be about 100. Let's look at that. 20.3 overs will be roughly, you know, about here. And yeah, that looks like that's about 100. Yep. But it asked me to use the equation, not just estimate off the graph. It asked, well, actually said use the line of best fit. So it doesn't matter which way I go there, because the line of best fit is the equation. I could have done it graphically, and just said, well, 100, bring it over, go down. I just got really accurate. If someone had done it graphically and just said, look, at about the 20 over mark, they'd be 100% correct. E, a cricket team's run rate is the average number of runs scored per over. Okay, I might have to take back that promise before. According to the linear model, what was the team's run rate? Okay, well, if the average run rate, or the run rate, is defined as the number of runs scored per over, that's exactly what we had. In other words, the gradient is runs per over. By definition, by looking at the units, it was that many runs per overs. We've got a gradient of 2.96 runs per over. That is the team's run rate, 2.96 runs per over. What are the limitations of the linear model? Well, I would say that beyond 50 overs, I'm not going to use this linear model, this equation, to predict 60 overs, 70 overs, because maybe they get tired. Maybe they don't go as fast a rate. You've also got to be careful. I don't like something else about this. And what I don't like is this part, early on. That wasn't an actual number. This was our first dot. We said after 7 overs, there were 60 runs scored. That was fact. Do you really believe that after no overs, there was 40 runs scored? I don't. If there were no overs, if there was no cricket played, they did not have 40 runs. Okay, I assure you. So the reality of this is they would have had 0 runs after 0 overs. So they must have just taken off really fast in a non-linear way. That's okay, but that's one of the limitations of the linear model. Sometimes it's not all linear. They might have been really consistent here, and it looks like they were consistent here, but clearly they had a big start. Okay, so a question like the limitations of the linear model, I always think about, look, we don't know anything that happens beyond. Maybe it tapers off, and we don't know what happened before the first result. I'm happy with my linear model between my first and last numbers. Between 7 overs and 45 overs, I'm happy. Beyond that, I'm not promising anyone anything. Okay, so how did I go with that? So see, look, I'm a scammer. It looks like I probably drew the line, so it was a perfect 3 instead of a 2.96. What I have, b equals 40. Okay, I did that in both times. So you can see my numbers are a little bit different. Instead of 188, it's 190. But anyway, it's the same thing. And we're on to the exercises. Okay, I hope that was helpful. Remember to jump on Blackboard at any time and ask questions. Pretty quick with the replies, or come to online tutes. But I hope it's a happy week 3. Okay, see ya.